All right, we are now recording, and I think this is unit 2, and we're talking about the decibel from hell. And I think we went over a couple of ways in which we can describe the decibel in terms of power or in terms of pressure. And if I share screen and go to my notes and pull them up here, I can squeeze that guy down, shrink that one down, pull up the notes. And I think last week we went through the first page of this. We talked about intensity measured in decibels, force, pressure is force over an area. We talked about that you could measure the decibel in terms of pressure, or you could measure it in terms of power. And I believe I showed you even a PowerPoint slide with 2 thermometers on it. And I said basically you can think of this thermometer as being pressure, and you can think of that thermometer as being power. And I said freezing is freezing is freezing. Boiling is boiling is boiling. In Canada, we call boiling 100 and we call freezing 0. In USA, you call it 212 and 32. We think you're crazy, but you don't. Anyway, the easier way to measure sound is in terms of pressure. But 120 decibels pressure is the same as 120 decibels power. And 0 decibels pressure is the same as 0 decibels power. It's just that power has 1 trillion increments in it, and pressure has 1 million increments in it. So the degrees are simply thicker in terms of pressure. But even that is too many ding-donged increments, isn't it? I mean, the ear can sense so many different intensities or pressures. So look at this graph again with me, and consider this horizontal axis to be the amount of pressure hitting your drum. And what did we say was 0 decibels at sound pressure level? We're dealing not with power, we're looking at pressure because we said power was too complicated and too busy. So here we have pressure units against the eardrum, sound wave pressure. What was the softest? And some scientists said, well, you know what? We have to define it as something. Okay, we can't say 0 decibels is the absence of sound, because otherwise you haven't defined what the ground is. And you need to define what is your 0. And we're going to call 0 the softest pressure it took for a normal hearing human to hear a 1,000 hertz tone at 1 meter distance with 2 ears. Those 3 conditions. Okay, whatever pressure was the softest in that condition to hear that 1,000 hertz tone, oh, it happened to be 0.0002 dynes per centimeter squared against the eardrum. Okay, that's the pressure. We're going to call that pressure 0 decibels sound pressure level. And if we increase that pressure by a factor of 10, we're going to call that 20 decibels sound pressure level. And if we increase it by another 10 and another 10 and another 10-fold, remember this is 10 times 10 times 10 times 10, so it's logarithmic. So 200 dynes per centimeter squared has 1,000,000 times as much pressure as 0, or 0.0002 dynes per centimeter squared against the drum. And 200 dynes per centimeter squared is about the maximum that a normal human can tolerate. That's at the threshold of pain. So from just barely audible pressure to pain pressure, well, that range is so big that we have to have a way to shrink it down. And that's why we do use logarithms of pressure to define decibels. So 120 decibels may look like it's 120 times 1 decibel, okay? But in all reality, 120 decibels represents 1,000,000 times the sound pressure that 0 decibels represents. And in that way, we've shrunk 1,000,000 units into 120. And that makes our hearing tests much more doable. And I said, I think I told you last week, oh, if you see 100, if you look at an audiogram, a hearing test, and you'll see 120 units on it, You go, oh, isn't that nice? But peel away the veneer and ooh, you got logarithms underneath. Put it back again. Okay, that's the knowledge we need to keep among ourselves. Your client doesn't need to know that, but we need to know basically what that is. Share screen again, Teddy, and let's look at some notes, and let's find out if I can tell you another set of lies. Here we go. So let's look over here. We all went down the first page last week, and then we talked, I think, about, way down here, we talked about 4 ways to assign numbers to things. And we said, well, you can name things with numbers, just randomly, or you can order things with numbers. That's a higher way. You know, you're ranking according to height or weight or intelligence or whatever, like hair color, whatever, okay? So ordinal is the next way, and that means you're not only naming, but now you're ordering along some dimension. And then we said a third way is like you're not only ordering and naming, but now you're saying equal intervals between each item that's ranked. And I think I said last week, ranking is often scary because advertisements will say, oh, we're the 3rd largest hearing company in the USA. Yeah, well, hearing aid company 1 may be here, hearing aid company 2 may be a little bit shorter, and hearing aid company 3 is like way, way, way behind. Okay, but the public is just thinking, oh, they're 3rd. Or what's the 3rd horse to make it around the track? Oh, well, horse number 1 and horse number 2 were neck and neck, and horse number 3 was a lap behind. Yeah, but he's the 3rd horse. Okay, so ranking is often misleading. Interval says not only are you naming with the numbers, not only are you rank ordering with the numbers, now you're saying that the ranked items also have equal distances between them, like inches on a ruler or degrees on a thermometer. Ah, and that is going to come up in your counseling course, believe it or not, because your counseling course next year is going to talk about questionnaires. How happy are you with your hearing aids in quiet? How happy are you with your hearing aids in traffic? Okay, and how do you assign feelings onto numbers? Well, interval scale, on a scale of 1 to 5. How happy are you with your hearing aids? 1 being fantastic and 5 being terrible. How are your hearing aids at the supper table? Give me a number. And hey, those are interval, because the distance between 1 and 2 is the same as the distance between 2 and 3, which is the same as the distance between 3 and 4. So now we've mapped your emotions, your feelings, onto an interval number system. And now they can shove the paper in a computer and do statistics. That's what questionnaires are based on, interval scale. Then there's a 4th and higher way than interval. Not only are you naming with numbers, not only are you ranking, not only do you have equal distances, now you've defined 0. You've said what 0 is, and that's the decibel. I mean, if you think if it's 10 degrees outside, is that twice as warm as 5 degrees? Not really. It's 5 degrees warmer than 5 degrees, but it's not twice as warm as. Okay? So when you're talking the decibel, you are defining what 0 point is, what that is. That's what makes the decibel a little bit complicated. People get a little bit bummed out once in a while with the decibel because it's got these stupid logarithms in it. But fear not, you're good, you're OTC. Then I said, you have to look at this weird little formula, because if you've got some pressure, we're going to call 0, remember, is always this guy right here, is always the denominator of the ratio, always. So the bottom number is always 0.0002. And so if you're trying to figure out what decibel is represented by some sound pressure, you've got some sound pressure. What is that in decibels? That's what your question is. If you have some pressure, you have to put that over the ground pressure to figure out what the decibels was, because remember, the dB is based on ratio scale. It's got a ground, and the ground is 0. And what is 0? 0.0002 dynes per centimeter of pressure. Okay, so first do the ratio, then do the logarithm of the ratio, then multiply that by 20. And I gave you two examples here. If you had 0.002 dynes per centimeter squared, what does that mean in decibels? Well, 0.002 divided by 0.0002 equals 10. How many times does 10 have to be multiplied by itself to equal 1? 1. 1 times 10 is 10. So the logarithm of 10 is 1. What's 20 times 1? 20 decibels, sound pressure level. Sure enough, if your pressure is 0.002, your decibels is 20. Back to your paper. Think if you have 0.02 dynes per centimeter squared. What is that in decibels? Well, 0.02 divided by 0.0002 equals 100. What's the logarithm of 100? Well, how many times does 10 have to be multiplied by 10 to equal 100? 2. 10 times 10. So the logarithm of 100 is 2. What's 20 times 2? 40. And if you look over here, 0.02 is 40 decibels. Okay, so just making sure that we keep a handle on that. And then I said, don't worry about this at all. This is just FNO, for nerds only. Okay, freak thou not out, yea, e'en so verily. Just leave it alone. Next. Here's a summary description, though. And this is what I said at the beginning. 120 decibel sound pressure level is the same as 120 decibels intensity level. Intensity is power, SPL is 0 decibels, SPL is the same as 0 decibels power or intensity level. But power, we said, has 1 trillion increments between 0 and 120. Pressure has 1 million increments between 0 and 120. That's the two thermometers. So power is pressure squared. In other words, 1 million times 1 million is 1 trillion. Okay, the square root of 1 trillion is 1 million. So I would put a star by that. You should know that just basically, but again, don't freak. Okay.
Can I ask a question quick?
Absolutely not. How dare you? No, okay, just a second. Okay, let me stop sharing here. Please do.
Actually, well, what you said there, that could you say what the SPL and the IL is again?
SPL is pressure, sound pressure level. And earlier and last week when we mentioned power, measuring sound in terms of power, that's dBIL, intensity level. And then we said, but power is work that's produced, whereas pressure is sound is something that's received, and the ear receives sound. So the ear is more like a receiving device. So the ear receives sound pressure. So guess what, power? Sayonara, bye. We're putting you in the rearview mirror. We're going to use pressure. And besides, pressure has only 1 million increments to deal with between 0 and 120, and power has 1 trillion. So screw that. It's way too many. So let's just talk about pressure. And that's what we do from now on.
SPL is sound pressure level.
Correct.
Okay.
Yeah. Yeah. I know power and pressure both begin with P. I know it's weird. But anyway, you got it. Okay. Share a screen again. And okay. So here's your little, this top of the page is just describing, again, how you do that formula. That's all it's doing. And here, this table here, that's just this picture here. Okay? This table is this picture. Is this table is this picture. I'll do it faster and cause a seizure, okay? No, there you go. All right. Go down the page. Double, and I will never ask anyone to figure out anything in terms of logarithms. We're not cranking out math students here, okay? I will, if I ever give you a question on a midterm or a final or whatever it is, I will ask you one of these examples, always keeping it in tens. Okay, always asking this stuff, these numbers, to convert into decibels. And I may ask you to please show work. So that should just tell me what you did and how you got there, so that you're not memorizing, but you worked it out in that little formula. Enough on that. Here's what we need to get to today. Look at this crap. Because of the logarithms, doubling the sound pressure does not double the SPL. Let me give you an example. If I take a 1,000 hertz tone and it's 10 decibels sound pressure level, and then I add a second 1,000 hertz tone at 10 decibels sound pressure level, the total isn't 20. Okay? The total is 26. You're looking at me going, okay, how come? Because of the stupid logarithms. That's why. Okay? It's those stupid logarithms. Bless you. I heard a sneeze all the way from Minnesota. All right. As they say in Hungarian, Egészségedre. I guess in German they would say Gesundheit. My better half is just coming home on the bike. You can see out of the window. Anyway, okay. Now, where was I? Oh, yeah. Now, if you have a 1,000 hertz tone at 10 dB SPL, and then you take a different frequency at 10 dB. So let's add a 2,000 hertz tone at 10 dB SPL. The result isn't 26 this time. Now it's 23. You're going, oh, God, what is he doing to me? Let's look at it and read with our notes. Go to the notes. If you have, for example, if you double the frequency, what is it? If you double the decibels, SPL, let me get that stupid square out, represented by 20, you don't get 40. 20 times 2 is not 40. You actually get 26. And that's only if both sounds are equal in frequency and equal in phase. Let me close the door here so I don't bother people. Hi, Kim. All right. But, so that's only if the two tones are identical. If you have a tone of 20 dB SPL and a different frequency at 20 dB SPL, add them together, your total's 23. Let's put it this way. What's average conversational speech in intensity? Does anybody remember that from last week?
60.
60 to 70. Good. So if Ted is talking at 60 to 70 dB, and all of a sudden there's two clones of Ted, okay, now there's Ted and there's another Ted, and both Teds are talking at 60 decibels, SPL. The total will be 66. Go up by 6. But let's say if Ted is talking at 60 decibels, and then Samuel talks at 60 decibels. Guess what the sum total is then? 63, because Samuel's different from me. He's got a different voice than me. Okay? Think about the logic here. How loud do people sing? La, 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 la. Oh, say, can you? And don't forget to bow or whatever during, like the football players are doing. You know what I mean? Anyway, if you're singing, let's say you're singing at 70 decibels SPL, and all of a sudden there's a choir. There's 100 people singing at 70 dB SPL. Do you think it's going to be 70 times 100 decibels? Or 100 times 70 decibels? Shoot, that's going to be 7,000 decibels. Screw that, you're going to blast people's eardrums out. It doesn't work that way. Okay? First of all, everybody in the choir is different. Okay? Second of all, if you increase the pressure by 100, let's look at that. What happens when you increase the pressure by 100? Look at the table here. If I increase the pressure by 100, how many decibels do you go up? 40. Okay, so if one person is singing at 70 decibels sound pressure level, and then 100 people are singing at 70 decibels, if they're clones of the one person, if they're identical, then you're going to have 70 plus 40. That's 110. But guess what? They're all different from each other. And because they're all different from each other, you won't even go up by 40. You're only going to go up by half of that. Just like 3 is half of 6, you're only going to go up by 20. So guess what your sum total is? 90 decibels. And that makes more sense. If you've got a church choir singing, and there's 100 people singing in the choir, yeah, the intensity is roughly about 100 or 90 decibels. Otherwise, it would be 70 times 100. That'd be 7,000 decibels. You'd have bleeding eardrums. Okay? So that's how when you add decibels together, they don't just double like that. Let me give you another example. You have a machine in a room, in the corner of a room, and the machine's making 80 decibel sound pressure level. And then you take the second machine and you put it at 100. She's making faces at me. Okay, so you have a second machine, and it's in the other corner of the room, and it's making 80 decibels SPL. It's not going to be a sum total of 160. And you can't assume that the machines are identical, because no two machines are identical. They're not producing exactly the same frequencies at exactly the same phase. So guess what? 80 plus 80 doesn't even equal 86. 80 plus 80 equals 83. Okay? This is all because of the decibel being from hell. It's based on log of frickin' rhythms. So this is what we need to get in our heads, okay? Back to our notes. Take a peek. So look at this. If you increase the sound pressure by 3 to 1, you go up 10 dB. If you increase the sound pressure by 4 to 1, you go up 12 dB. Oh, look at this one. If you increase the sound pressure by 10 to 1, you go up 20. Well, that makes sense. Look at this. If you increase the pressure by 10, by tenfold, you go up 20. Well, so you've seen that one before. Put a star by that one. Okay? 20 to 1, 30 to 1, 100 to 1. Oh, 100 to 1, you go up 40 dB. If you increase the sound pressure by 100-fold, you go up 40 dB. Well, let's find out. If I increase the pressure by 10 times 10, 0.02 is 100 times 0.002, okay? Or 0.02 is 10 times as much as 0.0002. And guess what I went up by? 40. So you've seen that before. It is no mystery. We're making history, okay? If you increase the pressure by 10,000 to 1, you've gone up 80. Well, let's go back to our thing here. 10 times 10 is 100, or 10 times 10 times 10 times 10. Okay, so 10 times 10 is 100, times 10 is 1,000, times 10 is 10,000. Well, you've gone up 80 dB. 10 times 10 times 10 times 10. So it just makes literal sense. If you've increased your pressure by 1,000,000 to 1, 1,000,000 to 1, well, 200 is 1,000,000 times 0.0002. So if I've increased my pressure by 1,000,000-fold, I've gone up 120. And that's exactly what it says on the table. Okay? So this table, and this table especially, this table here keeps it all in tens. Okay? This table here is giving you some dirt in between. And then from here, 100, and here, that's just a repeat of what you saw here. Okay? So, but this table is just a little different because it's talking a bit about some other kind of ratios that are smaller. That's all. But just know the point here. In real life, you are not adding tones together of equal frequency and phase. If you have two different frequencies of the same pressure level, adding them together increases the sound pressure by only half, 3 dB. So 45 dB SPL plus 45 dB SPL in real life for all practical purposes is 48, because no two sounds are exactly alike. Only in theory, if you were in a lab producing a 1,000 hertz tone at 0 degrees phase at 20 dB SPL, and then you added another exact frequency, an exact phase, then it would be 26. But otherwise it isn't. So here's your example. One guy talking at 65 dB SPL, 10 identical guys, you would increase the pressure by a factor of 20. Because when you increase the fact by 10, you've gone up 20 dB. So look at the graph. If you increase the pressure by tenfold, I've gone up 20. Okay? 10 identical guys talking at 65 dB SPL, you'd go up by 20. It'd be 85. But in all real life, if Ted was talking at 65 dB SPL, and then Renee and Samuel and 7 other guys join me talking at 65, my sum total would only be 75. Just like 3 is half of 6, 10 is half of 20. Also, in real life, you aren't always adding 2 equal decibel values together. Sometimes you're not adding 50 and 50, you're not doubling. Sometimes you're adding 60 and 50, 70 and 30. You may not be adding 2 equal decibels together. Then I'll stop sharing and tell you this right to our faces. 60 decibels sound pressure level plus 50 decibels sound pressure level is basically 60. An elephant plus a mouse is basically an elephant. If you weigh an elephant and it weighs a ton, and you put a mouse on the elephant's back and weigh the elephant, it's basically the elephant, right? Because the mouse is like, it's nothing. 60 decibels SPL is way bigger than 50. Why? Logarithms. It's those stupid logarithms. So 50 decibels SPL is an elephant compared to 50, which would be a mouse. In terms of pressure, because everything, increase the pressure by 10, by 10, by 10, by 10. So just realize that it's very weird. So just on any type of a quiz, if I ask you on a midterm, 40 dB SPL plus 30 dB SPL is equal to something closest to, you should say 40 dB SPL. Okay, if I say 40 and 30 and I give you a multiple choice and A says 70, well, no, that's not true because you're not adding decibels like that. They don't add together like that. You can't do that. Okay, dBSPL plus dBSPL does not just add like an arithmetic. It can't because of logarithms. And then if I said, so if I took 2 identical tones and added them together, how much do you go up by? You should say 6. If I say 2 equal but different frequencies, same intensities, add them together, how much do you go up by? 3. But what if you're adding 2 different intensities? What if I'm adding 60 and 50? You should say it's 60 and 50 is probably like 60.000 blah, blah, blah. You know, it's a tad more than 60. You're adding something to it, but basically an elephant plus a mouse is closest to basically the elephant. That's the logic I need you to understand. Enough on that. Next. Here's a couple of examples. 90 plus 80 is basically 90. And as soon as the numbers start to get smaller than 9, if the decibel distances between the two is less than 9, then you do start actually adding. So take a peek at this particular picture here. There, it's this one. Okay, to add 85 to 90. Okay, these are only 5 decibels different. It's not like 60 and 50. Those were 10 decibel different. Then an elephant plus a mouse is basically an elephant. But if the differences are less than 10, okay, so let's say, for example, if you're adding 85 dB SPL to 90 dB SPL, find the difference between the two numbers. It's 5. Find 5 on the curved line and follow this point horizontally to the vertical axis. And what do you get? Basically 1, 1.2. So I guess 85 plus 90 is 91.2. That's what you're adding to the biggest number. Find the difference between the 2 decibel levels. Find whatever that difference is, find that number on the curved line here, and go to the left. What is that? 1.2. I guess you're going to add 1.2 to 90. 90 plus 85 decibels is going to be 91.2. I guess. I'm not a mathematician. I'm not figuring it all out in formulas. But this picture is to highlight what happens when the decibel distance is less than 9 or less than 10. Table for guesstimating sum of decibel levels. Right here, if the difference between the two levels is 9 or 7 or 6, you know what I'm saying. If the differences are very, very little, okay, then you're going to be adding these kind of numbers. And this table comes from that picture. That's all it is. Again, don't freak. I won't even ask you this. It's just something you need to know, just to get an idea of. Here's something else to keep in mind about decibels. This is the last tricky or somewhat difficult, sort of a slippery thing. But then again, it isn't so difficult and slippery. It's this. Always remember, number one, look at number one first. 0 decibels SPL. I should put dB SPL in here, because there. Always remember that dB, and you do that too in your notes. Always remember that 0 decibel sound pressure level does not, repeat, not mean no sound. 0 decibels SPL is 0.0002 dynes per centimeter squared, and this is indeed something, even if it is tiny. Look, if I go to the picture here on your notes, let's go to this here. I can find a number smaller than 0.002. I can make it 0.001, 0.0000002. In other words, hey, what would happen if I put another 0 in front? I guess it would be minus 20 dB SPL. If I put another 0 in front, it would be minus 40 dB SPL. Put another one, I guess it would be minus 60 dB SPL. Just like taking away a 0, okay, taking away a 0, you go up by 10. You've increased your pressure by a factor of 10. You've gone up 20 dB, and keep taking away zeros. You've gone up, up, up by 20. Well, if I add more zeros behind it, so I make this even smaller, you go down, down, down. So always remember 0.0002 dynes per centimeter squared is some pressure. And what is that pressure? The softest required for a normal hearing human to hear a 1,000 hertz tone at 1 meter distance with 2 ears. That's how soft. Done. All right. Back to your notes. And that's what it says here too. So you can actually have negative decibel SPL values. I'm going to add SPL always here. Like minus 20. Okay. All right. Here's another thing. And this is what you and I are going to like. Let me stop sharing. You and I, we're going to like this one a lot. The only people who sit and mess with the fact that you can't add decibels together, like 1 + 2 is 3, are people who are doing sound level meter measurements in factories. People who are measuring machines in factories to determine whether the workers by law need to wear headphones. Those are the people that have to know all the physics, and they have to know that if you increase 2 tones identically, you go up by 6, and 2 machines that are different, you go up by 3, blah, 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 blah. You and I, though, we're fitting people with hearing aids. And in the hearing aid world, you can add decibels like 1 + 2 is 3. You know how? If you're adding dB to dB SPL. And you're thinking, oh shit, where is he going? Let me tell you. Look in the notes. Here's where we're going. You can add decibels sometimes, like 1 + 2 is 3. You can sometimes do it in some situations, and here's when you can. You cannot simply add 2 dB SPL. See, wherever I'm adding SPL in these notes, please you do too. Okay? You cannot simply add 2 dB SPLs together. Can't do that. Because if one machine is 80 dB SPL and the other one's 80 dB SPL, they're not 160. Sorry, it's 83. Okay? But that's because you're adding 2 dB SPLs together. In hearing aids, we don't do that. In hearing aids, there's 3 things. And write these down or else hammer them into your head somewhere. Input plus gain is output. And think of input as the sound arriving at your hearing aid. That's dBSPL. People talking, 60 to 70 dBSPL. People whispering, 50 dBSPL. Ambient room noise, 40 dBSPL. Traffic, 85 dBSPL. Sound coming into the mic of your hearing aid is called the input. And input is always called dBSPL. It's some dBSPL. Whether it's loud or soft, it's dBSPL. It's all different frequencies, but what's the intensity measured in? dBSPL. But what does a hearing aid do to the sound that it picks up? The hearing aid adds. The hearing aid adds muscle. It amplifies. And that amplification is called gain, G-A-I-N. Input plus gain is output. Now, gain is a relative thing. Gain is not referenced to the zero here. Gain is not referenced to this corner. Gain is relative, man. I can add 50 dB of gain to a 10 decibel input. I can add 50 decibels of gain to a 20 dBSPL input. I can add 50 decibels of gain to a 30 decibel SPL input. So the 50 is relafricative. It's relative. So because it's relative, I can add that gain to any particular dBSPL input. The gain is represented as simple dB, not dBSPL, just dB. And the sum of input dBSPL, the sound coming into the mic, plus the lift or amplification in gain, dB alone, equals the sum total output that's hitting your eardrum. Input plus gain is output. So output is the sound coming out of the hearing aid into your ear canal. And output is always dBSPL. So input is dBSPL, output is dBSPL, but the gain is relative. That's simple dB. So when you are adding a dBSPL plus a dB, it's like 1 plus 2 is 3. And that's what we do in our field. So we can, C-A-N, can add decibels like arithmetic. 50 decibels input, SPL, plus 50 decibels of gain, dB, equals 100 decibels SPL output. Get it? 50 and 50 is 100. As long as you're adding an absolute, which is dBSPL. And why do I call it absolute? Because all dBSPLs are referenced to this corner. All dBSPLs are referenced to that. That's why you did that ratio. Some dBSPL is equal to the logarithm of the ratio, 20 times the logarithm of that ratio. And what's the denominator of that ratio? It's always 0.0002. So all dBSPLs are referenced to this ground. But gain, that's relative. I can add 50 dB of gain to a 20 dBSPL input. I can add 50 dB gain to a 30 dBSPL input. And the gain is just relative. So 50 dBSPL input plus 50 dB gain equals 100 dBSPL output. Input plus gain is output. And that is our field. That's what's good to know there. That's that second point right there. All right. Now we've completed the hard part. That's the part, all the addition, the ratios, all that stuff, that's the hard part. Now let's coast down the hill and enjoy some easy peasy Japanesey. Okay, here we go. This is what you should know. Get an idea of it. a whisper at about 5 feet. What's ambient room noise? 40 dB SPL. 40. Ambient room noise, when I'm shutting up and I'm not saying a word. If I just sit here like this, the ambient room noise in your house is around 35 to 40 dB SPL. You're almost never hearing down to 10. That's the only way you'd hear down to 5 or 10 dB SPL is if you put yourself in a soundproof room, an anechoic chamber. Then you'd hear your lunch digesting. As I said, you'd hear every burp, fart, and whistle in your body. You'd start hearing ringing in your ears, okay? We've always got some sound hitting our ears, always. So ambient room noise, around 35 to 40 dB SPL. Back to your notes. A soft whisper, maybe 50-ish. Average conversational speech, 65 to 70, 60 to 70, anywhere in there. My father can beat your father at checkers, yakety, 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 yak, your mother wears army boots, okay? All right, shouting, 80 to 90. A lawnmower, around 100. Jackhammer, 140. Pain, 140. Okay, so just have a good idea of what these are, because there's a lot of stuff that's untrue that we talked about last week, highlighting indications of decibel levels. This one here, it's only really true. This here, the 60 is pretty good. That's quite true. But whisper, quiet library at 30, I don't think so. Ambient room noise is 40. So how could a quiet whisper be 30? So that's the BS territory, okay? If you go to another one like this, let's see if I've got more of those. Here, just audible sound, 0, yeah, that's true. Soft rustle of leaves being 10, I don't think so. And what's missing here is the dBSPLs. They're always supposed to be dBSPLs, they're not. They're just saying dB, you'd think these were gain. So whoever made this up is probably writing for some popular magazine or something. This isn't really not very true. It's just not very accurate. This is true. Normal conversation at 3 feet, 60 to 70. But all these should be read in dB SPL. All of them should. See if I can find another pack of lies. So, what I need you to really focus on is these levels. This is the truth. Compare that to the stuff you get in your PowerPoints, and you can tell falsehood from the truth. Okay? This little thing that says inverse square law, that just means sound decreases with distance. Well, that makes sense. I mean, if you go here, if I go to here, if here's the source, sound waves spread out. Okay, so you're going to lose intensity. The inverse squares law says that, hey, as you double the distance, you go down by 6 dB. Just like when you double the sound pressure, you go up by 6. Well, that would only be true if you were in a place where no sound waves bounced. If you were not in a room, if you were hung 100 feet above the ground, let's say, or you were talking and there was no place for your sound to bounce off of. But in a laboratory condition, perfect lab condition, sound intensity decreases by about 6 decibels as you double the distance. Inverse square law. But let's talk about protection of hearing loss and other and what do you call it, dangerous noise levels. Okay, that's what we need to concentrate on. So we're winding down here, just about done. Now you have things called, I'm going to show you this picture here. This is a good word to remember. I wish this black thing here would disappear. I hope, yeah, good. Go away. Okay. Earplug attenuation. Attenuation is the opposite of cranking something up. If you attenuate, that means you're turning the volume down. So circle that word in your notes or whatever. Think of that word, attenuate. Because that's what people talk about when they talk about earplugs, to protect against noise. So now if you look at this graph here with me, you'll see frequency along the horizontal axis, and you'll see decibels on the vertical axis of attenuation. and the dBs go down. So look at cotton balls. Let's say you took cotton batting and you squeezed it up and you jammed it in your ear canals. How much would it attenuate the low frequencies? Barely at all. How much would it attenuate the high frequencies? Maybe by about 10 dB. Okay? Let's say you took those foam earplugs. Oh, my internet connect. Those yellow squeezed foam earplugs. You know, the ones you see sometimes construction workers wearing or whatever. You squeeze those and you stick that in one ear all the way, and you just take the other one, squeeze it, and you jam it in the other ear. How much attenuation will you get? Well, about 30 decibels of attenuation for the lows, for the mids, and then even more than 30, around 40 decibels attenuation for the high frequencies. So you can tell that those foam earplugs are much better than cotton jammed into an ear. But here's something interesting. There's a set of earplugs like this called musicians' earplugs. Now, musicians' earplugs are really interesting because they attenuate, but they preserve the natural resonance of the outer ear. Now, if you look at this blue line here, and we've encountered this in our anatomy in 120. The outer ear and the ear canal, quarter wave resonators, remember that? And what frequencies does the outer ear, the ear canal being 1 inch long or 2.5 centimeters, we said, oh, because it's open at one end and closed at the other end, it's a quarter wave resonator. It's going to vibrate with sound waves 4 times as long. Well, that's true. So if you look at it in a graph, a picture here, guess what? Look at this blue curve. The outer ear and ear canal resonate with these high frequencies, with sound waves that are about 10 centimeters long or 0.1 meters long. Remember what wavelength equals speed of sound over frequency. Frequency equals speed of sound over wavelength. Your outer ear is going to resonate with these high pitches. Why? Because we speak and the high-pitched consonants are hardest to hear. All of this is from anatomy class. Back to acoustics. Musicians' earplugs. So these guys over here, where am I here? These kind of earplugs, they attenuate by about 15 decibels. And look what they do. They preserve that outer ear canal resonance, that natural way in which you hear. That's why these cost more than foam earplugs. They're special earplugs. They reduce, but they preserve that outer ear canal resonance. So musicians like these because everything's made quieter, but it's not muffled. They can still hear people talking pretty good because the high frequencies are still kind of let in. But you can see this whole blue line is pulled down, but the curve is preserved. Okay? They've taken the chain off the brain. So these are special earplugs, musicians' earplugs. They cost about $50 a piece. So musicians like to have these kinds of earplugs. So if you look at this earlier picture, a musician's earplug, it nicely attenuates flat by about 15 decibels right across. But what it's really doing is it's keeping the natural curve. Okay, before we run out of time, how much causes noise-induced hearing loss? This is the last thing we need to cover. By the way, sound level meters are used to measure sound intensity in factories. You and I don't do it. They're very expensive. They can measure down to 0 dB SPL. The expensive ones can. The cheaper ones can't measure that soft. Audiometers, which you will learn about in a bit, they are used to test human hearing in dBHL. You haven't covered that yet. That's another reference. Don't worry about it. Audiometers test human hearing at 6 or 7 octave frequencies, and I'll give those to you now. Write them down in the margin. 125 hertz, which is low C on a piano. The next one's 250 hertz, middle C on a piano. The next frequency is 500 hertz, high C on a piano. The next frequency is 1,000 hertz. The next one's 2,000. The next one's 4,000. And the last one is 8,000. Count how many frequencies you have. 7. So we test hearing at 7 different frequencies. Okay? 125. And notice that the numbers are doubling each time. When you double the frequency, you go up 1 octave. Okay? Recall, total range of hearing is 20 to 20,000 hertz. Audiometers, oh, there you go. It's written right there. What's the matter with me? All right, there you have it. The bottom is what we need to finish with here. Most states allow 85 to 90 dB/SPL exposure for up to 8 hours a day. As you increase the intensity by 5 dB, and sometimes the law is only 3 dB, the time of exposure gets cut in half. So for example, if in the state of Missouri, you are allowed to be exposed to 90 decibels for 8 hours, and then if you're exposed to more than that, you must wear earplugs, okay? If you were exposed to 95 dB/SPL, you would only be allowed to be exposed to that for 4 hours. If the intensity was 100 dB/SPL, you'd only be allowed to be exposed to that for 2 hours. So the bottom one is usually 90 or 85. Some states it's 85, some states it's 90. As you increase, that's the cutoff. As you increase the dB/SPL by 5 dB, the allowed exposure cuts down from 8 to 4, to 2, to 1. So if at 90 dB/SPL for 8 hours, 95 for 4 hours, 100 for 2 hours, 105 for 1 hour, 110 for a half an hour, and you know what I mean. Again, 120 would only be like 7 minutes. They don't allow you that, see? So again, it's all the stupid logarithms, but worry not. Earplugs attenuate. Not all the same. There's lots of different types. Ones that cover the whole ears are usually better than the little ones that sit inside the ears. And we've covered here musicians' earplugs versus regular foam earplugs versus cotton batten. Okay, there's all different kinds. But basically, we are at the end of our stuff here. Okay, here's some law. Here, 85 for 8. Well, look at this. In this state, it was as you went up by 3 dB. They cut the time in half. Just depends on where you are. But if I ever ask you this on a quiz or an exam, I will define what it is and then ask you to figure it out. If I say the cutoff is 85 dB/SPL for 8 hours a day, what would be the time exposure for, let's say, 105? And I would ask you to figure that out. You'd have to go up by 5, cut it in half, up by 5, cut it in half, and so on. Anyway, sound levels and human responses. Let's see what this says here. Rocket launching from a pad, 180 decibels SPL. Yikes. Oh, by the way, whenever you see that A, okay, that's just dB/SPL. Just don't worry, that's factory termination for dB/SPL. So 180, handgun right by your head, 166, rifle, fireworks, balloon pop, cap gun, firecracker, jet takeoff, boom cars, jet engine near, airplane taking off, noisy squeaking toys. Look at this one. They have laws now about this for babies. Squeaking toys, loud toys can cause permanent noise-induced hearing loss in children. So now people are becoming more aware of that. Okay? Thunderclap nearby, nightclub, boombox, stereos, all of them are around 120. Football game, stadium, It can get pretty loud. Oh, here's my pet peeve. Leaf blowers. Okay, let me have some cheese with my wine. Leaf blowers. They ought to be illegal. The stupid things. All you're doing is blowing your troubles onto somebody else. It's called a rake. Have you never heard of a frickin' rake? Rake your leaves and put them in a bag. Don't blow them onto my property. Like, anyway, every time I see those things, I just like, oh, would you please stop? Anyway, that's it for dB and intensity unit 2. Next week, we'll cover unit 3, complex sounds. We'll tie all the stuff together more. We'll talk about, instead of tones, we'll talk about speech, noises, like normal sounds. So then we finish our physical acoustics with 2 weeks on unit 3, next week and the week after. Then it's midterm time. Okay, so we've done, unit 1 was frequency, wavelength, speed of sound, period, all that crap. Unit 2 was intensity and the decibel from hell. Unit 3 is 2 weeks, and it's on complex sounds. If you have any questions, email me. Otherwise, ask me now or forever hold your peace. No, I'm just teasing. No one's getting married here. Anyway, are we good? How are you doing? Cool.
I'm feeling so-so on some of this stuff.
Do you have any particular thing you might want to ask? Anything in particular?
I was going to ask if you could just give us a couple of like sample questions that might be on the quiz or something.
Yeah, sure. Like, let's do that.
Mostly with the like the increasing the decibel and I don't know.
If I ask you a question, let's say if I say this, I might give you a sample question like this. I'll say a 1,000 hertz tone at 40 dB SPL is added to another 1,000 hertz tone at 40 dB SPL. They are both the same phase, frequency. What's the sum total dB SPL? Then you should say 46. Okay, because you've added 2, you've doubled, but everything's identical. I might ask you, a machine in a corner of a room is making 90 dB SPL. Then another machine is added to the room, and it's making 90 dB SPL. What's the sum total? Then you should probably say, well, no 2 machines are identical, so I don't just add 6, okay? I add 3. So the sum total would be 93. One machine's making 90 dB SPL, the other one's making 90 dB SPL, sum total is 93. I might ask you a question like this. Ted is talking at 70 dB SPL. Now another clone of Ted is talking in addition, and that clone is also talking at 70 dB SPL. What's the sum total dB SPL? And you should say 76, because one clone of Ted is identical to another clone of Ted. But if I said to you, Ted is talking at 70 dB SPL, and then Renee walked up and stood beside Ted, and he is also talking at 70 dB SPL, what's the sum total? And you should say 73, because Renee's voice is different from mine. Got it? Just like that. I'll say, if I increase the sound pressure by a factor of 10 to 1, how many decibels is increased? You should say 20. I should say...
Can you say that again?
Sure.
I don't understand that.
Sure. If I increase the sound pressure by a factor of 10, how many dB do I go up? Let me show you. On this favorite picture that we always show.
20 dB.
Yeah, up here, Ted. Go here, here. There you go. If I increase by 10, what if I increase the pressure by 10? Following my cursor from 0.002 to 0.02. I've gone up. My pressure is increased by a factor of 10. This has 10 times the pressure of this pressure. This pressure here has 10 times as much as that pressure. So if I've increased my pressure by a factor of 10, how many dB do I go up? The answer is 20. Here, from here to here, it's 20. If I increase it again by 10, how many did I go up? Now I went to 40. If I increase this by 10 again, how many do I go up? 60. So if I went from here to here, my answer is 60. If I increase my pressure from here to here, I went up by 80. So if I increase my sound pressure by a factor of 100, 10 times 10, how many decibels do I go up? The answer is 40. If I increase my pressure by a factor of 1,000, how many dB do I go up? You should say 60. If I increase my sound pressure by 10,000 fold, how many dB do I go up? 80. Okay, and so on. If I increase my sound pressure 1,000,000 times, how many dB do I go up by? 120. It's all about this graph and that table in your notes. Good, glad you're asking. These are questions. I'm glad people are asking questions. Do ask questions. That's the benefit of having good old Zoom, Zoom, Zoom. And I don't mean Mazda. Zoom, Zoom. All right. Holy rock, man. Okay. I'm feeling positively silly now. Anyway, ciao for now. We'll see you when we look at you. All right?
Thank you.
Cheers. Okay. Now I better stop recording.